word problems, right? How does this actually apply? So this entire section is all about applications of what we've been doing so far, why we do this. So motions in space, in other words, how does this all fit together, in our lovely world? So there's a couple of things we're going to be dealing with. So the first one is the very easiest one, is positions. So we cover this in calculus 1, right? Position functions, and we do all that fun stuff. Rates of change, so accelerations, velocity, and the speed, and the position functions. So guess what? This applies also to us as well. Okay. So we're going to slowly break through stuff down. Eventually we can, but we're going to start with the easiest one. What I mean by easy is, you've hopefully seen this already, right? So first of all, we'll go to the couple definitions, positions. So again, the same concept as before. In this case, because we have a vector, r of t will be our vector, right? So therefore the velocity, so this is going to be our position function, or position vector. V of t is going to be the derivative of rt, which is the velocity, and then a of t is the derivative of velocity, right? Or the double derivative of the position, right? So same thing applies there, right? So in Cal 1 we had s goes to v, that goes to a using derivatives, and therefore going backwards you just do integration, right? So this is derivatives, and this is integration. And then lastly, the speed of a particle, or the speed of an object itself, is going to be the magnitude of the velocity vector. So like everything else, the best way to deal with this is, okay, how do we do this in actual word problems, right? That's the best part. This is actual applications of it. So if the position of an object in a plane is given by this vector, find the velocity, acceleration, and speed when t is equal to 1. So we're just going to go straight forward, we'll just go one way. And you'll see we can go backwards. It's a little difficult itself. Okay. So let's just start from there. So given this is our position vector. We want to find v of velocity. So in other words, v is just the derivative with respect to t. Okay. So this is going to be the vector. So this derivative is going to be 1 minus 3t squared. This one's just going to be 3. And this is going to be e to the t. Now, since we're given a t value, we just plug it in. So v of 1 is going to be our vector of 1 minus 3 is negative 2, 3, and e to the 1 is just e. And there we go. And since we're already on v, we can just find its magnitude of the length. So this can be 4, squaring it 9, and then squaring that gives you e squared. So this is equal to the square root of 13 plus e squared. So we got velocity, speed, and now we got acceleration. So remember, acceleration is just the derivative of this. So just take the double derivative of this value here. So it's going to be negative 6t, 0, and again, e to the t. So this is when t equals 1. So now we plug in t equals 1. So our acceleration vector at t equals 1 of this particle or this object is equal to negative 6, 0, and again, e. Or the first are just e. And like I said, this is why I said this is start with the easy part, because position, velocity, and acceleration are actually the easiest of all of them, because they're nice, literally going one way or going backwards the other way. The other ones have different type of equations. This one has a nice, depending on the equation itself, but the format is always the same, just one way going down or one way going back up. Okay, so do one more example just like this. So same thing, given the position of the object now being this as our vector, same process, find all three itself. All right, so first find v of t. This time we don't have an actual time, so we're just going to do the general ones itself. All right, so take the derivative. E to the t is the same. And just for fun, if you noticed, I did a product rule here. Right, so f is t, g is e to the t. According to the project rule, it is f prime g plus g prime f, just in case you guys forgot. So it's going to be the derivative of t is 1 times e to the t plus t times the derivative of e to the t, which is still e to the t. So there's our vector. So then I'll just do acceleration, since the magnitude is going to be a little lengthy to do. So now take the derivative again. So negative 6t. Same thing. This part is just the same. However, again, it's product rule again. So since we already have the derivative, I'll just recopy it here. So notice we could put these together to simplify it. And there we go. And then finally, the magnitude. So if we square every single thing, this is now going to be 9t to the 4th plus 9 e to the 2t plus all of this squared. And you can just leave it like that. At this point, there's no point in simplifying. That makes sense as to why it does that. Everybody comfortable going that way? So definitely a test question like this would be nice if your teacher does it right. Right. So the difficult part is now going backwards, because integration is usually a lot harder to go backwards and forwards, right? Not only just integration, but given I want to find the position function from starting from the way of the acceleration function. So you have to do the double integration of it. So a particle starts with an initial position of r of 0 equals 1, 0, 0, or the vector of 1, 0, 0, with the initial velocity of that. If the acceleration is given to us to be this vector, we got to go backwards, find the velocity and position function at time t. Okay. Now, at time t, just remember, right, this is x, y, so t is equal to 0 in this case. All right, so to go backwards, right, so we have r goes this way is v, this way is a, so therefore we go the opposite direction is the integral going backwards. So we got to find the integral, so v of t will be the integral of our acceleration function. And I keep forgetting this is dt in each single one. That's going to be really important as I go forward. So I got to discipline myself to make sure I can put the proper notation in there as well. So taking the integral of each individual case. So this is going to be t squared, so 2t squared I plus t squared. So this is going to be 3j. And then lastly, it's just this 1, so it's just going to be t. Okay. So we got our velocity function, or velocity vector. Okay. Now, remember, we want to find, we're given an initial velocity, right? We're given an initial velocity of, so when t is equal to 0, we have this. Now, remember, when I take the integral of a velocity vector, I have a constant vector. See, so essentially, just like it was in Cal 1 and Cal 2 actually as well, since we're trying to solve for initial positions, we first want to solve for c before we take the second integral. So what that's saying is if I plug in 0 in for t, I get I, so 1i minus 1j plus 1k equals when I have t equaling 0 everywhere. So if you notice t equals 0, that goes away. T equals 0, that goes away. And then t equals 0, also that goes away. Look at that, that's kind of nice. So the only thing I'm really left with is a vector c. So my constant vector is literally I minus j plus k. Now, how do we put this together? So how do we put our velocity vector and our constant vector? Okay, so all we're going to do is add up each component together. So we're going to add this and this together. Well, technically there's an imaginary 1 there, right? So I'll just put 1s here so you can see. So it's going to be, my actual velocity vector is going to be 2t squared plus 1, because that's the constant term in front of the I. Keep going. 3t squared minus 1. And then finally, t plus 1 for the k value, for the k component. So that's how we do constants in vector format. We just add up each individual components to it. And now we take the integral of all this, because now since we got the vector function, that's the first part we wanted, right? Vector point. And now we want the position point. So we have to take integral of all of this again. So let's see, it's going to be the integral of each individual part again. And I ran out of room here. There's all those dt's everywhere, right? So integrate this is going to be t to the third power over 3 plus t. That's going to be the first component. So since I'm running out of space here, I'm just going to do it in vector format. Integrate this to the third power minus t. So that's a nice one. And then final over here, t squared over 2 plus t. And then we'll say plus the c vector there. And now we do the same thing we did over here. But now we're going to use our position vectors there. Okay. So what this is saying is, remember, this r of 0 is 1i plus 0j plus 0k. So that's what that equals. So if I plug in 0 in for t everywhere, I just have I itself. So if you notice, it's kind of the same template we're about to do here. So 1i equals, if I plug in 0 everywhere, I have 0i plus 0j plus 0k, plus again a constant vector. So therefore, the constant vector is only in terms of I. Now, let's say for, obviously we're not done, but let's say for a quick little hypothesis, we had this. Where the j and k were gone, just like, and we just had like a 2 there. So we would just solve for the I components, right? So therefore we would just subtract it over. So minus 2i, so we'd get minus I is equal to c there. So therefore, the vector of the constant is going to be -1, 0, 0, just in case you guys are wondering. You just solve in general. Okay. So just like over here, you would solve each component individually and each component of the C vector. So if this was like a 5, a 7, and a 2, you would just solve each one individually. So bring it over and then just solve for it. Okay. Because again, right, the C vector is like C1, C2, C3. So you could say like I is equal to 5i plus C1. So that's why you would subtract over and just solve for new components. So just in case you guys are wondering, I know this is a pretty simple example to go by, and not all examples are going to look like that. So to finish this up, so now that we know this portion, and all I'm going to do is adding 1 to the initial vector. So therefore, finally, our position vector of R of t is equal to 2t to the third over 3 plus t, and since it's 1, so plus 1, and that's the only thing I'm adding, so everything else is exactly the same. There we go. Any questions there? Okay. All right, so now we're getting a little bit more complicated. So actually, a little shortcut before we go any further. So there's a couple of shortcuts of this general solutions. So you're still going to have to take the integral twice. However, there's a little shortcuts instead of having this initial stuff all the time over and over again. And it's kind of like what I just did earlier, but with the proper notation is so the velocity function, or the velocity vector, sorry, is equal to the initial plus the integration of that. So notice that's exactly kind of what we did. I just brought this over, subtracted it, but it means the same thing because you're still find the CT term as well. And same thing applies here. So if you want to find the position vector, it's the initial, so this plus the integral portion. Again, if you actually have bounds, that's the key thing. So since we didn't have bounds, well, we kind of did, right? We 1 to 0 to 1 itself, but if we have the bounds itself, you could just do it as well. So fun little fact if you guys want to do that as well. That's a little shortcut. Instead of having to plug it in and figure out what the C value is and adding it, you're basically adding it to that as well. So this is considered the C. You find the C value here or C vector there in both cases without even knowing it. Okay, so that's just a little shortcut if you don't like, if this is too much or too complicated as well. Okay, so now we go into a little harder stuff, particle motion, right? So this is like the second type of way in single variable, and now in Cal 1 and Cal 2, we talked about derivatives and integrations. But since we're in 3 dimensions, we got a little higher. We have second law of motion, which is the biggest one. If you guys have taken physics before, this is a big one, is force is equal to mass times acceleration. Okay. Now, if you know taking physics, you know that force is actually a vector, and obviously we just identified the acceleration is also a vector as well, right? Mass is the only thing that's a constant because mass is, just the mass of the object itself. Okay. And we want to start, how do we get these type of situations happening? Okay. So let's just start with the easiest scenario. Let's go back to 2D to explain what's going on. Okay. So just like anything in our planet, he throws something up, comes up, and then eventually comes down, right? That's usually how it works. So therefore, if we start with force is equal to mass times acceleration, another way to write this in terms of the acceleration format is F is equal to negative m g j. Now, why the j component? Because as I go through this portion, right, let's say this point here, this is x comma y. What's being affected? as I go through this, according to the acceleration. Well, the x isn't, because x is just distance. So the y component is actually being affected the most, because that's the one being pushed down. Okay, so that's the reason why the j component is the only one in the what was it, in the ij components, or the x plane, as actually happening. Okay, so just in case you guys are wondering why a is only, so a in this case is the vector 0, 1, or again in this case, and j. So like I said, so the acceleration is just negative g j. Hence mass is just the, as a constant term itself. Okay. Now, gravity. So G, right? G is the gravity. We all know about gravity. That's the reason why we can't, jump up, and we always go back down. So we know gravity is a single value, again, itself. But again, since we're dealing with vectors, so gravity is equal to 9.8, we'll just say for short, right? And we'll put the unit just in case for your physics people that like units so much. That's how much gravity is. Now, this is essentially the same as the magnitude of 8. So therefore, we'll keep that in mind for short. Now, if I want to go backwards and figure out what's going on with respect to its position function, because we want to figure out what is position function across the board here, given only this, right? Going way backwards. In other words, doing what we just did in the last example. Well, we know the velocity, the derivative of velocity is a of t. Okay, so if we take the integral of that, well, g is just a constant. So the integral of a constant just gives you minus gt plus some c constant, right? Okay, that wasn't too bad. That's much easier than the last example. Okay. And just like the last example, speaking of it, right here, we're going to set c of t, so the vector of c of t, the constant term, to be v of 0, or just v naught, the initial velocity vector. So if I rewrite this now, I'll have my velocity vector is equal to minus g of t j plus v naught, the vector of the initial position. Yeah, isn't that interesting? Isn't that just what we just talked about earlier? Also crazy count. Anyways, we're almost done. So that's our velocity vector. Now we want our position vector, so take the integral one more time. So this is going to be minus g of t squared over 2 in the j component plus, well, this is going to be our initial velocity t, right? Because we take the integral of both terms, plus again another d vector. And remember, d vector is the constant because we just took the integral. And just like we said here, we're going to let this d vector to be the initial position of r naught, kind of like what we have here. Now, this is what gets pretty interesting. As I go around all the way here, what is the position, or what is the x component when it touches the ground? In other words, what is this? What vector is that? Well, there's two of them. Goes here. Well, x is going to be 0 because it doesn't go anywhere, right? It touches exactly on the ground, so that's going to be 0. And what's y? Also 0. So really, that's even better. That's exactly 0. So I'm not adding or subtracting nothing. So really, our position function is exactly this. There we go. So if you're wondering how in the world in physics class they were able to derive these type of equations, and they just plug and chug, or if you just didn't even care about if you took if you remember in Cal 1 how they derived these equations, well, this is exactly how they did it, using vectors. Now, because we're in multivariable and there's an alternative to do this, we have angles everywhere. So we have the angle at which this works. We'll call that theta. And this angle changes as we go along this line, given the point at a particular point, right? So this angle here would be different because I have a vector going out. This angle, let's say theta 1, would be different from this angle here, theta 2. Right? So now we put, well, given a particular point, we can actually find the angle itself or find the position function with the respective angle it makes. And that is exactly these equations. But if you noticed, it's very similar to what we just derived. The only difference now is because we have the angle of the vector mix, we have to incorporate that with the respective x and y component. So therefore, now we can get a little bit more complicated when it comes to our examples. So this one says a projectile is fired with a speed of 140 meters per second, and the angle elevation was 40 degrees from a position of 10 meters above the ground. A, when does the object hit the ground? B, how far did the object go? And what is the speed when the object hit the ground? Okay. So first we want to, when does the object hit the ground? All right. So let's write some stuff down. So it says a projectile is fired with initials with a speed of this. So this is our V naught. That's initial velocity. And this is our angle here. So this will, since I call it alpha, we'll call it alpha. So this is my angle alpha. It's a beta alpha. So now, when does the object hit the ground? Okay. So this is a little different. So we got to find the x component and the y component to see when it is actually hit the ground. So plug in what we have 140 times cosine of our angle of 40 degrees t. So don't remember what so cosine, let's see, my degrees, yes, my degrees. So cosine of 40 so let's say this is approximately 107 point, let's say 2 t. And the y component is a little harder because there's much more to do with, right? So 140 times sine of 40 t minus 1/2 g, which we know it's 9.8 t squared. Now, we actually did something wrong. Now, the reason why I say I think we actually did something wrong is because notice it says from a position 10 meters above the ground. So what does that mean? So that's saying I am starting 10 meters above the ground already, and then I fire the projectile. So therefore, I actually have to add 10 to the y value because I'm starting at 10, not at 0. And so that's just a little subtle hint for this type of problem. Okay. And now we just evaluate like we did for the x component. So now we do sine of 40 times 140. So we get 89 point, let's say 90 exactly. So 90t minus half of this gives you a 4.9 t squared plus 10. Okay. So now we still haven't answered the question. But the question says, when does the object hit the ground? So that means we got to solve for t. So x is going to be some distance. I don't know what that distance is, which is part B. So I don't know what that distance is, but I do know when it hits the ground, my y value is actually 0. So I'll just set 0 equal to y, and that means I'm going to have to solve for t now. Now you can use quadratic if you want, or anything you're comfortable doing. It really doesn't matter. You're going to get the same result either way. But in any case, you get approximately t equals 18.478. So looks like, yeah, seconds. So hit the ground in approximately 18.5 seconds. And therefore, now for B, how far did the object go? Well, that's the x component. So we want to figure out how far to go. So all I have to do is now just plug in t equaling that. So be 107.2 times 18.478. And that gives us about 19.8 point, let's say 8. So B is much easier once you get the A value itself, right? All right, now C. What is this speed when the object hit the ground? All right. So we're talking about speed. So first we need to find the velocity. But what is our position vector? Well, position vector is just the components x, y, which is right here. So 107.2 t, and then I'm just going to write that down for there. So then v of t is just a derivative. So 107.2, that's one component. And then the other component will be 90 minus 9.8. Oh, yeah, 90 t, and 10 goes to 0. So there's that. So therefore, the length or the magnitude of it t. What is t now, though? Oh, actually, before I get there, let me just, so it'll be 107, 2 squared. Plus, now before I square the next component, t. Now here's a key thing, when it hits the ground. So we know when it hits the ground, t is equal to 18.43. So before we actually get the magnitude, we can get this value automatically before we do any that stuff. So let's just quickly do that. So we get about, say that, I'm just going to round a little bit for magnitude's sake. So this is approximately 140 meters per second. Well, it actually gives you, let's say approximately, this actually gives you 140.69 meters per second, which is, yeah, look at that. Now, fair warning, that's not always going to coincide. Just be careful. Okay. So, any questions on this example? All good? All right. Next part is something called tangential and normal components. Okay. So this is a way to describe the acceleration in the form of a normal vector and a tangent vector. Okay, so it means like why? Well, why not, right? I always say that. So we could describe the acceleration of any acceleration given a normal vector and a tangent vector, or both of them, or vice versa. Okay, so in other words, we're going to see how can we create the acceleration by only using normal vectors and the acceleration only using tangent vectors. Okay, so essentially what's happening is if I have some acceleration vector here, this is my a vector. So therefore my normal vector is going this way. And my tangent vector is doing this. Right, so let's say this is the curve itself we're dealing with. So as you can kind of tell, that's interesting, because maybe if we take the normal vector, we get the tangent vector, or if we get the normal vector of the tangent this, we get that one. So there might be some correlation between one or the other. Okay? And their factor actually is. You actually derive one with the other one. But that's for now. Let's just first start with our tangent vector. So going back a section, we know the tangent vector is equal to this. However, we just found out that the derivative of r is the velocity vector. And so if we take the length of this velocity vector, that means, well, let's just start there. So if I plug this everything in, so I'm just going to call the length of this velocity vector some vector, let's call that, what's a good letter? W. Let's call it W. We haven't used W yet. So therefore, I can rewrite all of this to have V on top over W. And if I just solve for the velocity, that means just multiply it over. I get that. Okay. Well, remember, we want to talk about the acceleration, right? Not velocity. So to find the acceleration, that means we just got to take the derivative of this side. So we're just going to take the derivative d dt of both sides. So on this side, I'm just going to split it over. So on this side, we get, I'll just rewrite it, it's fine, a of t, which is what we want. However, on this side, because they're two different vectors, guess what we got to do? Product rule. So using our product rule, we'll have w t prime plus w prime t. Okay. All right, so we have something nice, but we have a problem. I don't know what t prime is. But we have an equation that has t prime in it. That's the curvature, the horrible one. So the curvature is equal to like that. Okay. And if we just solve for this, that means, again, just bring this over. And again, knowing that this is just w of t. So we'll just have w times the current of the curvature equals this length of t dt. Not dt, well, essentially, yeah. Okay, almost there, right? Our goal is to get this, but we have that. So how do we get rid of this horribleness here, right? That's the question. Okay. All right. One more thing. Don't worry, I promise. Okay. Now, we said we wanted a normal vector. We haven't talked about that yet. We have been doing the tangent vector. We've been following this process. Now, what is a normal vector equation? This goes way back a couple sections. We'll look at that. I multiply this over, and I have an equation for that now. Okay, now we're going to put this right here and substitute it. So finally, we know what the derivative of the tangent vector actually equals to. And it's the multiplication or dot product of the normal vector times the curvature times wt, or the length of the velocity vector. So therefore, doing all of this horribleness, remember, the whole point is to get this down. Our acceleration vector is equal to this part, which we can get, because that's not too bad to do, plus, now, instead of t prime, I'm going to put this instead. Yeah. Now, I already had a w, and I multiply by another w. So this is going to be this vector squared. Now, before you say why, oh, why, oh, why, oh, why, oh, why, oh, why. Okay, so this part right here is called the tangential vector. This part right here is called the normal vector. Of the acceleration. Okay. Now, don't worry, each one is done separately because just like everything else in math, we show you the hard part. We show you why do I have to find the curvature? That's horrible already. Why do I have to find the normal, which is also horrible? And I also got to find the tangent and some random, length of the vector itself. Well, not exactly. Just like the curvature of a curve, we could set it up to being just a respect to R, which make things a lot easier to deal with. Okay. So now let's using this new way of it to describe the acceleration of a particle or position. Let's use this stuff. So the position of a particle is equal to RT equaling t to the fifth, t squared, and t to the third. Find the tangential and normal components of the acceleration. So in other words, find each one individually. So hopefully you notice the most work is going to be this cross product here. That's going to be the most work we're going to deal with. Everything else is pretty straightforward, right? We could do derivatives, and the length of derivative is pretty straightforward. Just keep it inside the square root. So let's try this out. So first off, let's find the derivative of R. So it's going to be 5t to the fourth, 2t, and then 3. And since we need the second derivative, I'll just do that quickly as well. Zero is always nice, right? I like zeros. Okay, so we need the length of R in both scenarios. So I'm just going to write that down. So we need the length of R. So that's just going to be each one squared. So, so 5 squared is 25. T to the squared, so it could be 8 plus 4t squared plus 9. I'm just going to leave it inside the square root. And now for the tangential vector, or tangential acceleration of the tangential vector, we need the dot product of this and that. So remember, the dot product is multiplication and add, right? So this times this, plus this times that, plus that times that. So 5 times 20 is 100. T to the third times t to the fourth is t to the seventh. What was it? This times this is going to be 4t, and that's 0. Okay, cool. So therefore, our acceleration of the tangential vector is going to equal to this divided by that. Ooh, what am I doing? There we go. So that's the easy one, believe it or not, right? Now let's go on to the normal one. So the only difference between what we just did and what we need is, to the dot product, we need the cross product. So we're just going to quickly do the cross product of the derivatives. So again, I'll just set this up. So this one's nice because they have a 0 here. So a lot of stuff actually cancels, which is great. So for example, for the I component, you're just left with, so for the I component, we're just left with that. So you're just left with 6. For the J component, that 0 times 5 goes away, so you're just left with 60. And then for the K component is the only one that's got a little nasty for, is the multiplication of that. So it's going to be 5 times 2 is 10, minus this times that. So 10 minus 40, so 30, negative 30. To the 4th. Okay. Anybody verify that? Pretty sure. I'm going to look quickly. Sorry. 10. Yeah, I think that's it. Positive 60? The J? Oh, no, because remember it goes I minus plus. So this is a positive 60, so should minus in there. Yeah, that should be a negative 60. Okay. All right, now we're just going to find the magnitude. So magnitude of it. Again, this looks horrible, but remember, you could just leave it just the same way it is. So 6 is easy. It's 36 plus 3,600 t to the squared, so times 2, so 6 plus 3 times 3 is 9 t to the 8th. So finally, the acceleration vector according to its normal component is equal to all of this horribleness divided by that. And again, if you notice, if you're given a point like t equals 0, this makes life a lot easier, right? I just want to give you guys an example when you would have to do it in general, because, you know, physicists love general equations. Questions there at all? Yeah, you can leave it like that. I'm not gonna simplify it. Just it's a horribleness, you know. Well, you can't really simplify anything anyways, right? You know, this is unfactorable. You can't really do much. Unless you know, I give you like if t is equal to 1 or 0, you just plug it in and it makes life so much simpler. You would get an actual answer for each one, right? But yeah. All right, so let's try one more. And believe it or not, I actually brought this down a little lower. I had a harder question and it just made the equations horrible. So, you know, same thing. Let's make it a little easier for ourselves. We're gonna drop it down. So same process. Given the particle, oh, wait a minute. Oh yeah, no, that's right. What I'm talking about. So tangential and acceleration. All right, so do the exact same thing we just did above, right? So I'll do the exact same steps. Take the derivative, So it'll be 20 t to the fourth, -1, and then 3. So double derivative. This is even nicer. If you notice, 4 times 20 is 80. T to the third, 0. Oh, even better, right? It's going to make that cross product even nicer, right? Okay. So we need the length of R prime. So this squared, this squared, this squared. So it's 4,000 t to the 8th plus, oh, plus 1 plus 9. So that gives you plus 10. So now we're going to make the dot product. So this times this, added. So 8 times 2 is 16. T to the 7th. Everything is 0. So, oh, even better, right, to look at. So there's nothing to add to that. So therefore, maybe I should get in this example first, huh? Make it much easier. So the dot product over the length of the derivative.